Section 9.3, the algebra of functions. In this section, we'll be talking about ways to somehow, starting with a function, to get another function by using some operator on it, such as addition, multiplication, composition. And so, let me first define addition of two functions. And so, suppose f and g are two functions. Then I'll define f plus g, and I'll define it pointwise as just equaling f of x plus g of x. And this is where, well, I've defined how you define the rule of f plus g, but I haven't really defined told you what the domain is. So where the domain of f plus g is just equal to the domain of f intersect the domain of g. So I've both given you the rule and I've given you the domain. So I've given you what the function is. Let me define scalar multiplication. So let C be some scalar, some real number. Then let me define CF, where f is some function, by the following rule. CF evaluated at x is just the constant c times the function f of x. And this is where the domain of CF is just the same as the domain of f. And let me assume here that c is not equal to 0. Let me not write that. So let me define the additive identity. So I'll define the additive identity, the 0 function, as being such that, well, at any point x, the function is just equal to 0. And this is for all x. Let me define the additive inverse. Of course, the additive identity has a property that if you add a function to the additive identity, then you just have the same original function. So f plus 0 is equal to f. Let me define the additive inverse. So the additive inverse of some function f, I'll denote it by minus f, will be defined as the scalar multiplication of f with the scalar negative 1. Let me define multiplication of two functions. So suppose I have a function f and a function g, then I'll define f times g by the following rule. F times g evaluated at x. Let's define it pointwise as just f of x times g of x. And this is where the domain of f times g is just equal to the domain of f intersect domain of g. So where the domain of f times g is the domain of f, intersect domain of g. So in order for f times g to be defined, well, f x has to be defined at f and at g. X has to be defined for f, and f has to be defined for that particular value of x, and g has to be defined for that particular value of x in order for f times g to be defined. Okay, the multiplicative identity. For this particular multiplication of functions would be defined as, well, the function is defined as equaling 1 for all values of x. Let me define the multiplicative inverse. And so the multiplicative inverse of g, I'll define it as 1 over g, is just equal to 1 over g of x, where the domain of the multiplicative inverse of g is just equal to the domain of g, take away the kernel of g, where the kernel of g is defined as the set of all x such that the set of all x in the domain of g such that g of x is 0. So I can define division as multiplication by the reciprocal. And maybe I should tell you exactly what the domain is. So where the domain, maybe I'll make it even bigger. So where the domain of f divided by g is equal to, of course I'm assuming here that g is not 0. So where the domain of f divided by g is, well, the domain of f intersect the domain of g, take away the kernel of g. So you want x to be defined for f and for g, but you do not want to divide by 0, so you do not want that g is 0 at x. Subtraction. So f minus g is defined as f plus the additive inverse of g equality of functions and so f is equal to g if the domain of f is the same as the domain of g and f of x is equal to g of x for all x in the domain of f, or g, doesn't really matter because they're the same thing. Okay, so now let me give you some field properties. So with these definitions, basically functions act like rational numbers. And so let me give you the field properties. And so first, it satisfies the closure property for addition. So this says that if f and g are functions, so let's assume f, g, and h are functions, so f and g being functions implies that f plus g is also a function. The closure property for multiplication well, it's the same corresponding fact for multiplication. If f and g are functions, then f times g is also a function. Commutative property for addition. Which says that if f and g are functions, then f plus g is the same as g plus f. We have the commutative property for multiplication. Which says that if f and g are functions, then f times g is equal to g times f. We have the associative property for addition. Which says that if f, g, and h are functions, then f plus g added to h is the same as f added to the sum of g and h. We have the associative property for multiplication. Which says that if f, g, and h are functions, then f times g multiplied by h is the same as f multiplying the product of g and h. we have the existence of a additive identity. So there exists some function, the additive identity, such that for every function f plus the additive identity is just equal to the original f. And so this is a right additive identity. And by commutativity, we also have that the additive identity plus some function f is just equal to the function f. And so it's both a right and a left right and left additive identity. And so f plus 0 is just f, 0 plus f is just f. We also have the existence of a multiplicative identity. And so there exists some function called the multiplicative identity, such that for every function f times the multiplicative identity is just the original function f. And so this function, denoted by 1, is a right multiplicative identity. And by commutativity, property for multiplication, we also have that it is a left multiplicative identity. And so this is a multiplicative identity. We also have the existence of an additive inverse. And so for every function f, there exists a additive inverse denoted by negative f. And this has the following property, so such that any function f plus its additive inverse is the additive identity. And so this is a right additive inverse. Similarly, by commutativity property for addition, I have that it's also a left additive inverse. Existence of a multiplicative inverse well, for any non-zero function, there exists a multiplicative inverse denoted by 1 over f, such that if I multiply any function times its multiplicative inverse, it is equal to its multiplicative identity. Similarly, and so this is a right multiplicative inverse. Similarly, it's a left multiplicative inverse. And so if you multiply the multiplicative inverse times the original function, you get the multiplicative identity. And last, multiplication distributes over addition. So if you have any function f, g, and h, then f times the quantity g plus h, f times the sum of g and h is just equal to the sum of the product of f and g and the product of f and h. And so these are the field properties which we gave back when we were talking about numbers back in section 1.1, or well, back in the first chapter. In addition, these functions also form what's called a vector space. And so not only do they form a field, but they form a vector space. So let me give you the vector space properties. So again, let's suppose that f, g, and h are functions. And I don't know, let's say a and b and c, a, b, and c are scalars. So a, b, and c are scalars. In this case, we're probably thinking real numbers. We could, in the future, talk about complex numbers. There's some members of a field. And so so scalar meaning that they actually satisfy all the same properties of a field that we just gave for above. Okay, so first, closure for addition. So we've already given that property. Actually, a lot of these properties will be almost the same as for a field. And so, well, if f and g are functions, then f plus g is also a function. Next, the closure for the scalar, which in this case is a field multiplication. So the closure for scalar multiplication. So if c is some scalar and f is some function, then c times f is also a function. Next, the commutative property for addition. If f and g are functions, then f plus g is the same as g plus f. The associative property for addition. And so if f and g and h are functions, then f plus g added to h is the same as f added to g plus h. The associative property. For scalar multiplication. Which says that if a and b are scalars and f is a function, then a multiplying the product of b and f is the same as the product of a and b times f. the existence of an additive identity, the zero function. So there exists some function 0 such that for all functions f, f plus the additive identity is just f, and the additive identity plus f is just f. The existence of the scalar identity there exists a number 1 a scalar such that 1, the scalar identity, times f is just equal to f. The existence of an additive inverse. For every function f, there exists some function, call it minus f, the additive inverse of f, such that f plus its additive inverse is the additive identity. So this is a right additive inverse. And by commutativity of addition, I have that the additive inverse plus the original function f is equal to the zero function, the additive identity. Next, scalar multiplication. Distributes over addition. So let C be a scalar, let f and g be functions, then C times the sum of f and g is the sum of the scalar product of C times f with the scalar product of C times g. And lastly, multiplication distributes over scalar addition. So suppose I have two scalars, let's say a and b, then the sum of a plus b times the function f is the same as the function addition of the scalar multiplication of a and f added to the scalar multiplication of b and f. So those are the vector space properties. And so functions act like vectors. And they also act like members of a field. Let's do on page 367, problem number 2. So f of x is equal to 2x squared minus 1. G of x is equal to x squared minus 4. Okay, so in exercises 1 through 14, use the given functions f and g to find a, f plus g, b, f minus g, c, f times g, d, f divided by g, e, 2 times f, 3 times g, g, 2 times f plus 3 times g, and h, 2f minus 3g. Okay, so there's several parts to this particular problem. So first let me do part A. I want to find f plus g. Well, let's look at the rule. The rule is just take f, add to it g. And so this is actually equal to, I can combine like terms if I want. 2f plus 2x squared plus x squared is just 3x squared. Minus 1 minus 4 is minus 5. B. F minus g. Well, f minus g is defined pointwise as f minus g, which is just equal to 2x squared minus 1. Change, since I have a minus outside the parentheses, change all signs inside the parentheses. So this minus makes the x squared a negative x squared. And this minus makes the negative 4 into plus 4. 2x squared minus x squared is just x squared. Minus 1 plus 4, so 4 minus 1 is 3. And that is your answer. Let me do part C. F times G. Well, this is just 2x squared minus 1 times x squared minus 4. Maybe I'll multiply it out. So this is equal to, let's multiply, use the distributive property. And so 2x to the 4th minus 8x squared minus x squared plus 4. And so I get 2x to the 4th minus 9x squared plus 4. Combine like terms, since negative x squared minus x squared is minus 9x squared. Let me do part D. F divided by G. Well, that's just equal to F. 2x squared minus 1 divided by G. X squared minus 4. And that is your answer. Let me do part E. 2f. And so let's multiply 2 times f, which is 2x squared minus 1. Let me multiply the 2 inside the parentheses. And so I get 4x squared minus 2 f, which is 3g And so let me okay, that's F. So 3G. So that's just 3 times G, which is x squared minus 4. And so let me multiply the 3 inside the parentheses. And so I get 3 x squared minus 12. Let me do part G, which is 2f plus 3g. Well, I know what 2f is. 4x squared minus 2. I know what 3g is. 3x squared minus 12. And so combine like terms, I get 7x squared minus 14. And that is your answer. Lastly, let me do H, which is 2f minus 3g which is just 2f, 4x squared minus 2 minus 3g, 3x squared minus 12. And so, let me remove my parentheses. I have 4x squared minus 2. I have a minus sign outside the parentheses, so let me change all the signs inside the parentheses. So you get a minus 3x squared plus 12. 4x squared minus 3x squared is x squared. 12 minus 2 is just 10. Okay. Let me do well, that's really about it, I guess. All the other ones are very similar. You just plug in. So let me, yeah. Let's recall substitution. So let's say that we have y equals 3z squared minus 7z plus 1. And let z equal 4x plus 3. Now, let me substitute z into y so that I get y in terms of x instead of y in terms of z. And so I have y is equal to 3z 4x plus 3 squared minus 7z 4x plus 3 plus 1. And so I have substituted for every time I see a z, I replace z by 4x plus 3. Okay, so now let me introduce the concept of composition. Well, composition is just substitution. But in this function form that I've given you. Okay, and so say we have some x, and I have z, and I have some rule g that takes x and gives me g. And suppose I have another rule f that takes z and gives me y. Okay, so now if I take these two rules and instead of having them separately, where the rule G takes X to Z and the rule F takes Z to Y, I'll have one rule that takes X to Y. I'll call that, oh, and maybe I should. Maybe I'll give it a little different color here. Maybe I'll put it in red. Have this rule that takes X and gives us Y. Well, we'll give that a new name. That rule will be named F of G. So F composed with G is a rule that takes X to Y. And so, let me do this as sets. So suppose I have here X, Y, no, let's call this Y, and let's call this Z. Okay, and suppose I have some X that's mapped to some Z by some rule G, and I have some rule F that maps Z to Y. Then I'm going to define a rule F composed with G. Okay, so let's do that formally. So let G map X to Z and let F be a mapping from Z to Y. And so let these be rules. Then the rule defined by, well, the rule F of G, which maps X to Y, defined by F composed with G at X is equal to F evaluated at G of X. Well, I've told you the rule, but in order for this to be a function, I also have to tell you the domain. So with the domain of F composed with G is equaling the set of all x's, which are in the domain of G, such that G of X is in the domain of F, is called the composition of F with G and is read F of G. Okay, so notice that Well, in order for f composed with g to be defined at some x, well, first, certainly x has to be defined for g, so x has to be in the domain of g. But once it maps here, z must be in the domain of f, and so g of x must be in the domain of f. So that's why we have this relationship here as being the domain. Note, in general, f composed with g is not the same as g composed with f. And so this composition is not in general commutative. So it more or less acts like a multiplication, but it's a non-commutative type of multiplication. Okay, so identity function. The identity function is actually the multiplicative identity for composition, for if I consider the algebraic operation of multiplication to be composition. And so the identity function, denoted by ID, just takes every x and gives us back x. And so this is for all x. Note the following. Well, it does act like the multiplicative identity for multiplication, for the idea of composition as multiplication. So the identity composed with f is just f, and f composed with the identity is just f. So notice that this does indeed act like a multiplicative identity, or well, let me see, a composition identity. Okay, so let me do an example. Let f of x equal 3x squared minus 7x plus 1. Let g of x equal 4x plus 3. Then let's determine f composed with g at x. Well, wherever I see an x in the formula for f, I replace every x by the formula given by g. And so wherever I see an x in this formula for f, I replace x by 4x plus 3. And so this is just equal to 3 times the quantity 4x plus 3 squared minus 7 times the quantity 4x plus 3 plus 1. But note the following. At like 10 minutes ago, I told you that composition was really just substitution. So if you look at my function here, oh, now it's way up here. Aha. I let f of x equal 3x squared minus 7x plus 1 and g of x to equal 4x plus 3. Then I said that the composition of f and g is 3 times the quantity 4x plus 3 squared minus 7 times the quantity 4x plus 3 plus 1. And so if I just wrote each of these in functional form, I get back the exact same answer. And so indeed, composition is just substitution. This is just a very fancy way of saying substitute. On page 367, let's do, say problem 22. F of x equal x squared minus 9. G of x equals 2x minus 3. Okay, so in exercises 15 through 35, compute A, f composed with g of x, B, g composed with f at x. So let's do that. So let's do f, so part A, f composed with g at x, try this again, f composed with g at x. So wherever I see an x in the formula for f, I replace x by the formula given by g. So wherever I see an x, I replace x by 2x minus 3. And that is your answer. Let me do part B. And so I want to do g composed with f at x. So wherever I see an x in the formula for g, I replace every x by the formula given by f. So wherever I see an x here, I replace x by x squared minus 9. So I have 2 times x, which is x squared minus 9, minus 3. And that is g composed with f. So notice that f composed with g is indeed not equal to g composed with f. So it hardly ever is. Only very, very, very occasionally will they be the same. Let me do problem number 16. F of x equals 4x minus 1. G of x equals 2. Part A. F composed with g at x. So wherever I see an x in the formula for f, I replace x by the formula given by g, 2. So I replace every x by 2. Well, 4 times 2 is 8, minus 1 is 7. And so f composed with g is always equal to 7. B. G composed with f at x. Wherever I see an x in the formula for g, I replace x by the formula given by f. Well, there is no x. Therefore, g composed with f is always equal to the value 2. Let me do problem number 36. F of x is equal to 2 over x minus 1. G of x is equal to 1 over x squared. And so, in exercises 36 through 39, compute A, f composed with g at x, B, g composed with f at x. Give the domain in each case. So this is identical to what we did above, but now we also want to determine the domain of these functions. So let's do f composed with g at x. And so, wherever I see an x in the formula for f, I replace every x by the formula given by g. And so this is just equal to 2 over, I replace x by 1 over x squared. And that is your answer. Let me determine the domain of this function. So to find the domain, well, I want to set the denominator to 0. Well, in this case, I have two denominators, so I want to set x squared equal to 0. And I want to set one over x squared minus 1 equal to 0. Okay, so I have here x is 0. Let me add 1 to both sides of my equation. So 1 over x squared is 1. Multiply both sides of my equation by x squared. So I have that x squared is equal to 1. So, subtracting 1 from both sides, I have x squared minus 1 is 0. This is a special product formula, so I can factor this as difference. The product, the sum and difference of two terms is the difference of squares. So x minus 1, x plus 1 equals 0. Set each factor to 0 and solve for x. So adding 1 to both sides, subtracting 1 from both sides, I get x is equal to 1 or x is equal to negative 1. Okay, so the domain of f composed with g is, well, the set of all x's except for 0, 1, negative 1. So it's everything except for 1, I'm sorry, negative 1, 0, or 1. And that is the domain of your function. And I usually am pretty sloppy, and I would say the domain of f composed with g is just a set of all x's not equal to negative 1, 0, 1. And just assume that you could figure out what that meant. And so it's a pretty sloppy notation here, but well, this is what I mean. It's everything except for negative 1, so does not include negative 1, doesn't include 0, doesn't include 1. Let me do part B. G composed with f at x. Okay, so g is 1 over x squared, and f is 2x minus over x minus 1. So this is 1 over x squared. Okay, so let's try to find the domain of this. You set the denominator to 0. Well, this whole denominator can't be 0, but this can be 0. So set x minus 1 to 0. Add 1 to both sides. So x is equal to 1. Therefore, the domain of g composed with f is the set of all x's except for 1. It is, so if you want to write the domain in interval notation, it is everything except for 1. So it's all real numbers except for 1. Oh, we could also say that it is all real numbers except for the singleton 1. That's also another way to write the answer. I will be lazy and just write the answer this way. Let me do problem number 42. F of x equals the square root of 3 minus the square root of x plus 5. In exercises 40 through 45, write the function f of x as the composition of two functions, g of x and h of x. Okay, so there are a lot of possibilities here. So I'll give you maybe a few possibilities. So I want to write f as g composed with h. So I don't know, let g of x equal radical 3 minus x, h of x equals, well, radical x plus 5. And that gives me a way to write this complicated function as the composition of two simpler functions. I could also have said, well, let g of x equal radical 3 minus radical x, and let h of x equal x plus 5, then f then f is equal to g composed with h, or I don't know, let's say let g of x equal radical x and h of x equal 3 minus rad x plus 5. Then f is g composed with h. Or maybe I'll just give you one more, or sort of the trivial one, g of x equals rad 3 minus rad x plus 5, h of x equals x. So that one always works. Oh, maybe I'll give you also the one last one, which again also always works. Let g of x equal x, h of x equal the original function, 3 minus rad x plus 5. So I've given you, was it like 5 different ways of doing it? 1, 2, 3, 4, 5. Yeah, 5 ways. 1, 2, 3, 4, 5. So I've given you 5 ways of writing some function as a composition of other functions. Okay, let me do problem number 50, which is, well, functional notation. In exercises 46 through 53, compute A, f composed with g at 1, b, g composed with f at negative 2. Okay, so let's evaluate each of these. So A, so f of x equals rad x squared plus 1, g of x equals 4x minus 1. So let's do part A. I want to compute f composed with g at 1. Well, let's compute first g at 1. So wherever I see an x, I replace x by 1. 4 minus 1 is 3. Next, let me compute f at 3. I'll replace every x in the formula for f by 3. 3 squared is 9, plus 1 is 10. Therefore, f composed with g at 1 is just f evaluated at g of 1. But we found that g of 1 was 3, and f of 3 was rad 10. And so your answer is rad 10. Let's do part B. I want to evaluate g evaluated at f. G composed with f evaluated at negative 2. So let's compute f at negative 2. So I'll replace x by negative 2. And so I get 4 plus 1 is 5. Next, compute g at rad 5, which is 4 times rad 5 minus 1. Therefore, g composed with f at negative 2 is, well, f of negative 2 was rad 5, and then g evaluated at that value, which we found was 4 rad 5 minus 1. And that's your answer. Let's do problem number 52. So x, f of x, negative 3, 7, negative 2, 5, 0, 1, 1, negative 3, 2, negative 5. Let's do G. One zero, 2 1, 3 2, 4 3, 5 4. Okay. So I want to compute a f composed with g at 1. And so I'll input for x 1, find the output for g, make that as an input for f, and find the output. And so if I have an input of 1, then I have an output of 0, make that the input for f, that gives me an output of 1. So note that 1 was mapped to 0 by g, and 0 was mapped to 1. And so f composed with g maps 1 to 1. Let's do part B. G composed with F at -2. And so, well, maybe I'll use brown. Okay, so I have an input of -2 for F. That gives me an output of 5. I make that as an input. For G, my output is 4. And so, G composed with F at -2 is 4. So you note here that -2 is mapped to 5, and 5 was mapped to 4 by G. And so -2 is mapped to 4 by G composed with F. Okay. And so that finishes off section 9.3.